Hey guys, Dr. Kruse, teaching a little algebra here. I want to go over distance versus time graphs versus velocity versus time graphs. These two are related. I want to take a look at those. And I also want to introduce the concept of the derivative. All right, so first we need a definition for velocity. Lots of times velocity and speed are used interchangeably, and they're not exactly the same thing, especially when you get into maybe calculus or physics. They want you to know the difference between velocity and speed. So technically, velocity differs from speed. They sound like the same thing, but they're not. Speed is your rate of change, and in any direction. It doesn't matter whether you're going north, south, east, west, away from home, towards home. It's just how fast you're going. Rate of change, that's your speed, like your speedometer in your car. Your speedometer in the car is measuring speed. It's saying you're going 60 miles an hour. It's not telling you what direction you're going. It's not telling you if you're going north, south, east, or west. It's just going to say 60 miles an hour, your rate. Whereas velocity is basically your speed and direction. It's your rate of change, that's your speed, in a certain direction. So now you're going to say something like, I'm going 10 miles an hour north, or I'm going 15 miles an hour west, or I'm walking away from home. That would be my direction, away from home at 3 miles an hour, something like that. All right, so there's a little difference between speed and velocity. Lots of times people think they're the same word, but I just want you guys to realize that velocity is speed, but it's also where you're going. All right, away from home, north, whatever, a direction. So for example, if you jog north and then you rest and then you jog back south, like you go back home or whatever, your speed jogging north maybe was 5 miles an hour. That's a pretty fair jogging speed. And then you rest. Well, when you're resting, you're not moving at all. So your speedometer says 0 miles per hour. And then you get up and go back home and you're 5 miles an hour again. So notice the speedometer says 5 miles an hour, 5 miles an hour. But velocity has direction attached to it. So north, whatever the first direction they bring up, or if they say you're going away from home or whatever, or going north, wherever they begin, that's going to be your positive direction. So in this case, north would be a positive speed, 5 miles an hour. Now, when you're resting, you're not going north and you're not going south. So we don't have any direction on this, so there's no sign in front. There's 0 is neither positive nor negative. And our speed is 0 because, of course, we're resting. And then we jog back home. Well, we are going 5 miles an hour. That's our speed. But now we're going south instead of north. So since we've reversed our direction, we reverse our sign from positive to negative. All right. Another example, you walk to the library, you study for a while, and then you walk back home. All right, what's your speed? Well, a good walking speed is about 3 miles an hour. Walk into the library. Now, when you're sitting there studying, you're not moving at all. So your speedometer says 0 miles per hour. And then you walk back home at the same rate or the same speed, 3 miles an hour. So notice speed doesn't change. They're both 3 miles an hour. But velocity adds direction. All right, this would be, you could say this is away from home is plus, and headed back home is negative. Or you could say going to the library is plus and coming back from the library is minus. All right, but just make sure you label where you're going with your speed. When you're talking about velocity, which way are you going? I'm going away from home, I'm going back home. And here I'm just sitting here studying, so there's no positive or negative. All right, so now that we kind of understand what velocity is, I'm going to give you a real simple problem, and we are going to graph your directed distance. That means distance away from home and distance back home. And then we're going to graph the same data in terms of velocity right below it. So notice on our x-axis, our time is measured in hours, 1 through 9. Same thing with our velocity graph. Our time is still measured in hours, 1 through 9. So I'm going to measure the distance from home as 9 hours goes by, and then I'm going to measure your velocity as 9 hours go by. All right, so let's start with graph of distance, directed distance, distance from home. So maybe you have a story like this. You hike 6 miles north in 3 hours. Maybe you're hiking away from home or you're hiking north. You rest 3 hours and then you hike back. So now you're going south or you're going back home at the same speed. All right, well, a little easy math here. 6 miles in 3 hours, that's 2 miles an hour. So after 1 hour has passed, I have gone 2 miles. 2 miles per 1 hour. It's kind of like slope. I'm going to be bringing that up a lot today, all right? It's a lot like slope. I went 2 miles over 1 hour, okay? Next hour goes by, I go 2 more miles. So I was 2 miles away from home, and now I'm 2 miles further from home after another hour. I'm right here, all right? So now I'm 4 miles from home. Let's let another hour go by. So another hour goes by, and I go 2 more miles. So I was 4 miles from home. I go 2 more miles over another hour. Now I'm right there. Okay. All right. I'm sitting at the library, or, let's say we're going to the library. You rest 3 hours. I guess you're hiking. You're not going to hike to the library. So you're out in the woods, you rest 3 hours, have a little picnic, whatever, and then we'll hike back. Well, while you're resting, you are not getting any further from home. So after 3 hours, I was 6 miles from home. But for the next hour, I was sitting still. So I'm still 6 miles from home. And for the next hour, and for the next hour, for those 3 hours, 1, 2, 3, as 3 hours go by, I just stay 6 miles from home because I'm just sitting there not moving. And then I get up and I pack up and I start walking back home at the same speed. Okay, so after 6 hours, I'm 6 miles from home and now I'm getting ready to walk back home. So as another hour goes by, I walk 2 miles, but closer to home. So I walk 2 miles closer to home. Now I'm only 4 miles away. Another hour goes by, I'm 2 miles closer. Now I'm only 2 miles away from home. And then finally another hour goes by, and I'm 2 miles closer there. I'm back home. All right, let's go ahead and connect those with a line and just see what it looks like. All right, so you might make a note that this is kind of a linear graph. This is a line going uphill, that's a line going horizontal, and that's a line going downhill. That's going to be 3 different slopes or 3 different velocities that we're going to talk about here in a second. So let's move on to our next graph. All right, the graph of velocity. We're going to use the data from our story and our distance to graph our speed as time goes by. How fast was I going here? How fast was I going here? And so on. All right, so my graph of velocity, I'm just going to take this right off the table here. After 1 hour had gone by, I had gone 2 miles from home. That's 2 miles per 1 hour. All right, that's up to over 1. Just think slope. Kind of think like, what's the slope of this line between these 2 points here? Well, I go up to over 1. That's 2 miles per hour. So after the first hour, I have gone 2 miles per hour. And I've maintained a constant speed. I mean, from my very first step, I was going 2 miles an hour, 2 miles an hour, 2 miles an hour, 2 miles an hour, 2 miles an hour. So all the way from my very first step through that first hour, I was going 2 miles an hour. Same thing for the second hour. From hour 1 to hour 2, the second hour here, I'm still going up to over 1. I'm going 2 miles an hour, 2 miles an hour, 2 miles an hour, 2 miles an hour, all the way up to hour 3. I'm doing a constant 2 miles an hour. My speed is constantly 2 miles an hour. My velocity is constantly 2 miles an hour. So for the first 3 hours, I'm going 2 miles an hour. Okay. All right, let's think about what's happening here. What's my speed? Well, velocity would be a better term. What's my velocity as I'm sitting there at the library? Well, it's 0 because I'm sitting still. I'm not moving away from home. I'm not moving closer to home. 0, 0. So speed, 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 or velocity, velocity, velocity would be a better term. You can also think slope is 0. That's a horizontal line. The slope from here to here is 0. Slope is 0, slope is 0. There's lots of ways you can think about it, but thinking about it in terms of slope is often easier to understand. So slope 0, slope 0, slope 0. So my velocity for those next 3 hours is 0, down here at 0 miles per hour. See, velocity in miles per hour, 0 miles per hour. 0 after that hour, 0 after that hour, 0 after that hour. This is called a step function back in junior high. You can kind of see it stair-stepping. In fact, I'm going to go ahead and connect it. Whoops, that's not a straight line. I'm going to connect it so it kind of looks like a stair step. It's a step function. And now we got to figure out what's happening for our final 3 hours. All right, you're walking back home at 2 miles per hour. All right, 2 miles per hour. The thing is, you're going to have to make this negative. Now, this kind of makes sense, all right? If we're walking away from home, that's an uphill slope. That's going to be a positive slope, a positive velocity. If I'm sitting still, that's a horizontal line. That's a zero slope. That's a zero velocity. And if I'm heading back home, that's a downhill line. That's a negative slope. That's a negative velocity. So I'm going 2 miles per hour negative. This is a -2. So I drop down here to -2. From 6 to 7, I'm going -2 miles per hour. From 7 to 8, I'm going -2 miles per hour. And from 8 to 9, I'm going -2 miles per hour. Okay. All right. So some things to note about this graph is if directed distance is linear, your velocity is constant. Let's look at that on the graph. If directed distance is a line, that's what linear means. If directed distance is a line, so we have a line for the first 3 hours, well then your speed, now I keep saying speed, your velocity will be the same. That's what constant means. So if your directed distance is linear, your velocity will be constant. If your directed distance is linear, your velocity will be constant. Here it's constantly 0. And if your directed distance is linear, if it's a line, your speed, there I said speed again, your velocity will be constantly -2. So a good note is if directed distance is a line, your velocity will remain the same, will be constant. If directed distance is increasing, that's going uphill, well then your slope, think slope is positive, so your velocity is positive. If your directed distance graph is decreasing, that means going downhill, well then your slope or your velocity would be negative. That makes sense. And then finally, at the top there, if the directed distance reaches a maximum, so at the top of the graph, we call this a maximum. If it reaches the top, the velocity is 0. And it works the same if it reaches the bottom. If we had the picture of a valley, if we had the picture of a parabola, maybe a U shape at the bottom, we would call that a valley or a minimum. Same thing. The velocity is 0 at the bottom. All right, but what if my directed distance graph is not linear? What if it's a curve of some kind? What do we do then? So for example, you throw a ball straight up in the air at 100 feet per second or so, and it hits the ground 10 seconds later. So you threw it up in the air as hard as you could. It goes up there, it hovers for just a split second, and then it falls back to the ground. Assume the speed of the ball changes by 20 miles an hour each second. Now that's not exactly right, all right? You guys that are physics majors or calculus majors or whatever, you know it's slowing down and speeding up by increments, all right? But I'm going to make this a really easy introductory problem, and we'll just say that as each second goes by, the ball slows down 20 miles an hour. That'll give us a good curve to work with. So we start down here on the ground, the ball's in my hand, I throw it upwards at 100 feet per second. All right, now we're going to measure this as distance from ground. That's going to be our positive velocity here in a minute when we graph the velocity graph. So after 1 second goes by, I have gone 100 feet because it was going 100 feet per second. Think slope, 100 up 100 over 1. 100 over 1 is 100. So the slope from this point to this point is 100 feet per second. That's going to be our velocity on the next graph. All right. But gravity grabs that ball. You threw the ball up in the air. It doesn't go 100 feet per second forever. Gravity grabs it and slows it down. And I said, well, let's just pretend it slows down by 20 feet per second each second. So the next second, it was going 100 feet per second for this first second. But for the next second, it slowed down. Its speedometer slowed down from 100 feet per second to 80 feet per second. So after 2 seconds, that second, I only go up 20, 40, 60, 80 for the next second. And if it slows down again, then I only go up 20, 40, 60 for the next second. And then if it slows down 20 again, I go up 40 for the next second. And then if it slows down 20 feet per second one more time, I go up 20 and over 1, and I'm at the top of my curve. All right. So after 5 seconds, I've reached the top of my peak. All right, this is a maximum. And now gravity's going to grab me again, and it's going to start pulling me down slowly at first. Just watch the slope of the curve. It's going to pull me down slowly, but then it's going to speed up, get steeper, speed up, speed up, speed up. And down here, it's pretty steep and going pretty fast. So let's just kind of calculate that real quick. I'm going to go over the next second. I'm going to go 20 feet per second, 20 feet per second. That's going to be negative 20 feet per second in velocity speak. Next second, I'm going to go 40 over the next second. So that's going to be minus 40 per second. The next second, 20, 40, 60. Now it's going 60 feet per second for the next second. 20, 40, 60, 80. Now it's going 80 feet for the next second. And then finally, it's back up to its original speed, 20, 40, 60, 80, 100 feet over the next second. And you see that kind of makes a nice parabola. Let's go ahead and sketch that in. All right, so if we connect the dots, we see that this is not linear at all. It looked like it started out being kind of linear. That looks like a straight line there. But as the speed slowed down, it kind of pulled the line over. It kind of curved the line. And then it slowed down a little bit more, so that makes the line curve more until finally it curves and starts going downhill. So the reason this is not a line is because our slopes keep changing. This is 100. This is 80, this is 60, this is 40, this is 20. And then going downhill, this is negative 20, negative 40, negative 60, negative 80, and negative 100. We're just calculating the slope between each set of points, and the slope is changing between each set of points. All right, let's transfer that data to a velocity graph. All right, so let's think about what our speed is, what our velocity, I keep saying speed, what our velocity is as the same 10 seconds go by. All right, we have the same x-axis, time in seconds. 10 seconds go by, this one's measuring distance, this one's measuring velocity. All right, so I transfer my data, my velocity data, all right, and think velocity. When you think velocity, just think slope. What's the slope between the first set of points? That was up 100 over 1. So my velocity was 100 feet per second. My slope was 100 feet per second. So when time was 0, that ball left my hand at 100 feet per second, but it immediately started slowing down. Over the next second, from 1 to 2, it only went 20, 40, 60, 80, up 80 over 1. That's 80 feet per second. So it slowed down to 80 feet per second. And then between the next 2 points, it slowed down to 60, slowed down to 40, slowed down to 20. So it slowed down to 60, 40, 20. And then finally at 5 seconds here, I'm at the top. And remember, the slope at the top is 0. The velocity at the top is 0. So at 5 seconds, I'm on my x-axis. My x-axis is 0. And then after that, my velocity is negative. It's kind of the same speed numbers, but they're going to be negative because I'm falling back to the ground. So I start gaining speed slowly at first. I just go down 20 over 1, that's negative 20. Down 40 over 1, that's negative 40. Down 60 over 1, negative 60. Down 80 over 1, and then down 100 over 1. So my speed is increasing in a negative fashion. After 6 seconds, I was going 20 feet per second in the negative direction. After 7 seconds, 40 feet per second in the negative direction, negative 60, negative 80, and negative 100. Let's go ahead and connect those. Okay, we got a nice line on our velocity graph. So some important things to note. If your distance graph is going uphill or rising or increasing, if they use any of those words, well, of course, your slopes are all going to be different on this one, but they're all going to be positive. So your velocities will be positive if your distance is increasing, all right? Your velocities, even though they're all different speeds, those are all positive numbers, positive 20, positive 40, and so on. Your speed, I keep saying speed, your velocity at the top, that's horizontal, that's slope 0. Your velocity at the top is 0. So anytime you reach a peak or a valley, if this parabola was upside down and U-shaped, you'd be at the bottom of a valley. Anytime you're at the top of the mountain or bottom of the valley, your velocity is going to be 0. So at 5 seconds, my velocity was 0. At 5 seconds, my velocity was 0. I was right here on the x-axis. And then after that, it goes negative, which means that if your distance goes downhill, If your distance is decreasing or lessening or going downhill, well, those slopes are all negative. Now, they're all going to be different negative slopes, but they're all negative. Negative 20, negative 40, speeding up, speeding up, speeding up in the negative direction. So a good thing to note, all right, if your original distance graph is rising, all the slopes will be positive. If your original distance graph is falling, all the slopes will be negative. And then if you've reached a peak or a valley, your slope will be 0. All right, the last thing I want to cover is I want to introduce the concept of a derivative. All right, a derivative is a term they use in calculus. All right, you guys that go further in math, you'll talk about the derivative. The derivative is not that tough of a concept. It's kind of scary because nobody's ever seen the word before. But I just need you to think of I just need you to think of it as a slope. Specifically, it's an instantaneous slope. It's the slope at an instant in time. It's not the slope between 2 points anymore. It's the slope at a moment in time. So think of it as instantaneous slope. It measures the steepness at a certain point. So we're still kind of doing slope, but we don't have 2 points. For example, if I have this curve here and I call it f, and I wonder what the derivative is right here, all right? All I'm asking is, what is the slope at this point? I don't have 2 points that I can calculate slope at. I just have this single point here, and I'm wondering what's the slope or the velocity at this moment in time. All right, here's a better picture of what we're asking for. Let's start here. All right, so here's my same curve f. Here's the point I was asking about. I wonder what the velocity or the slope or the derivative is right here. Now, I don't have 2 points. Now, there is a way, you guys will learn this in calculus, there is a way to kind of approximate it. You start with a point far away, all right, and you calculate that slope, but then you make the point get closer. You just follow the curve and do a point closer on the curve and calculate slope and make it get closer and closer and closer and closer until finally the distance between the two is virtually 0. So start with a point, get closer, 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 closer. As that distance approaches 0, you're essentially talking about 1 point. So that's kind of a calculus thing that you guys will learn later. For us, we are essentially finding the slope of a line that is tangent. If you guys remember tangent line, that's a line that's outside the curve that kind of skips off the curve in just one spot. It doesn't touch the curve in 2 spots. It just barely hits the curve and kind of skips off it and just keeps going. So a tangent line touches the curve in 1 spot. So if there was a way to find the slope of that tangent line, let's say, for example, that the slope was up 4/5 of this tangent line, well, that means the instantaneous slope at this point would be 4/5. All right? So that's just kind of a simple explanation of derivative. Derivative is what is the velocity or the slope at a particular instant in time, instantaneous slope, the steepness at a point. So I could have a derivative here, a derivative here, a derivative here, a derivative here. They're all going to be different, all right? It's measuring how steep the line is at that point. All right, now there's lots of ways of saying this. If I say, oh, the slope is up 4/5, or I could say the slope is, subtract the y's divided by subtract the x's. That's rise over run that you guys learned in junior high. Or a shorter way of writing slope is the change in y. That's delta. Delta means the difference in the y's. Difference means minus. So delta means the difference in the y's, or the change in the y's, over the change in the x's. Delta y over delta x. That's a shorter way of writing your slope formula. Or I can call this thing a derivative. I can say it's the derivative of y over dx. And what I'm saying is the difference in the y's over the difference in the x's. The derivative of y, and now I'm saying as time goes by, or with respect to x. Your x-axis is usually time. So as those seconds or hours or minutes go by, what's happening with the slope is kind of what I'm asking. So the derivative of y, that's the slope at a point, as, with respect to x, as x changes. Another way to say it is maybe I call the graph f, like I did up above. The derivative of f with respect to x. You know, what's happening to the slope of f as time goes by, or at a certain moment in time. And another way, it just depends on your word problem. Maybe you're doing a profit problem, and the amount of profit you make depends on how many widgets you make. So it could be the derivative of profit with respect to the number of widgets you make. Maybe you're climbing a mountain. It could be the derivative of elevation. You know, how fast is your elevation changing? What's the change in your elevation velocity? What's the rate of change of your elevation with respect to time? All right, as time goes by, how is your change in elevation changing? All right, so just a final page of notes here. If I'm talking about the graph f, what does the derivative look like? The derivative of f, this guy, the derivative of f, you know, as x goes by, or at a certain x. Just think slope. Whenever you see derivative, think change in y over change in x. Just think slope, but it's called the derivative. It's the slope at a certain instant, at a precise x. Let's say, for example, you have f, this function here that's curving upwards, and let's say f is increasing, all right? So if it's increasing, my slope is going to be positive. It doesn't matter if that dot is there, or here, or here, or here. Any of those dots on this curve, the slope will be increasing. It'll be a positive number. Now, all of those slopes, all of those derivatives will be different, but they'll all be positive. So my derivative of f with respect to x is positive. Going downhill, it makes sense. Any point on this line, not just this point, any point on this line is going to have a negative slope, or a negative velocity, or a negative derivative. Not just this point, but any of them, all right? All of these points have different derivatives, have different slopes, but they're all going downhill, they're all negative. All right, if your graph reaches a, let me get all that on there. If your graph reaches a valley, all right, so you're going negative derivative, negative derivative, negative derivative, negative slope, negative slope, negative slope, 0, and now it's going uphill. Positive slope, positive derivative, positive derivative, positive derivative, or positive, 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 0, negative, 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 negative. All right, if it reaches a valley or a peak, right there at the bottom or the top, your slope is 0. You can call it the derivative is 0. At this moment in time, not a half second before, not a half second after, at that moment in time, your derivative is 0, your slope is 0. Same thing here, not a half second before, not a half second after. At this moment in time, your slope is 0. Your derivative is 0. That's instantaneous slope, the slope at a particular instant, the slope of f at a particular time. All right, same thing with the horizontal line. It doesn't matter if it's this dot or this dot, this dot, this dot. Every slope on this line is going to be 0. All right, there's no change. All right, so a good note, this is our last note here, is if f is linear, so if your graph of directed distance is a line called f, I'll note that on this one here, I just made the slope 1/2, up 1 over 2, up 1 over 2, up 1 over 2. So the instantaneous slope at this point is 1/2, and the instantaneous slope or derivative at this point is 1/2, and the derivative at this point is 1/2. So if f is linear, then your derivative is always going to be the same number. In my case, it's 1/2, but it just depends on the slope of your line. If your graph is a line, then your slope never changes. Your slope is constant, no matter which point you're at. All right, guys, that's it for today.